All right, week 4 of distance learning. So today we're going to take a look at area of regular polygons, so hexagons, pentagons, things like that, and then also composite figures, so taking what we've done so far and putting them all together into an odd-looking shape. So things we're going to see today: center of a regular polygon, radius of a regular polygon, apothem, central angle of a regular polygon. So central angle is similar here as it is to a circle. It's just with going to vertices instead of the edges of the circle. Radius, same idea as well. It's just one of the legs of the central angle, and then center of a regular polygon is just the middle. The apothem goes from the center to the middle of the edge of the polygon, and it is perpendicular to that edge as well. The composite figure, figure built by multiple different items. So here is kind of our process of figuring out just the ways we need to actually find the area of a polygon that's not one of the ones we've already seen. So first thing we need to look at is just the words that go along with it. So center, radius, an apothem, and the central angle. So we want to find those things, and we're also going to actually go ahead and find the measure of the central angle using our old knowledge of circles as well. So, or polygons, yeah. So here we're just going to name all these things. The center is X, pretty easy. That middle point. The radius, again, goes from the center to the edge of, or the vertex of the polygon, or the edge of the circle that goes around it. So there's a couple options here. We got XQ and XR. Those are the two that we see here. And then we also have an apothem. There's only one showing here. It's a weird word. It makes me feel like I have a lisp when I say it. Like I'm talking about an opossum, but it's apothem. So apothem here is from X to N, XN. And the central angle, remember we name angles with three letters. So central angle is going to be QXR. You can go the other way, RXQ. I'm not going to write it both ways because it's the same angle. And then it wants us to find the measure of the central angle. So we know, again, looking back, if you remember back to when we were looking at polygons before, the central angle of a polygon is based off of the 360 degrees, right? If you're looking at the interior angles, that's different. But the central angle, you just take 360 and you divide it by however many sides there are. This is a pentagon, so there's 5 sides, and that gets us 72 degrees. Now, if we wanted to find the angles that go around it, there's 5 of them, but there's not 360 that they add up to. It's a different number. So we'd have to actually figure out what that is. So it'd be 3 times 180, 540 divided by that. It's 108. So that's how big those ones are. But we'll need that here in a little bit. So the second one here, we are finally looking at to find the area of this tabletop that is a regular hexagon, side length of 3 feet, an apothem of 1.7 feet. So we want to find the area of it, and so you can see it's split up into 6 equilateral triangles, right? It is a hexagon. That's kind of the advantage of hexagons, is that they create equilateral triangles, but really we don't even need to know that, right? At this point, we know that we can see the apothem of it is 1.7. That's the height of one of the triangles. So if we take the number of triangles, so there's 6 triangles. Remember, the area of one triangle is the base times the height divided by 2. In this case, our height would be 1.7. Our base is 3. The height is 1.7. And we divide that by 2. So that's going to give us a decimal, 2.55, not an ugly one at least. So that's the area for one triangle. So then we multiply that by the number of triangles there are. There's 6. So the area of the pentagon is going to be that 2.55 times 6, which comes out to be 15.3. It does say to round to the nearest tenth, so 15.3 feet squared. So that's it. So let's look at what we just did, right? We did the perimeter, or well, hold on. We did the base, or that's the side, right? The base here is the side. The height is the apothem. And then we multiply that together. And then divide it by 2. And then we multiply that by the number of sides. So we multiplied the side length times the apothem times the number of sides, so that's n, times 1/2. So if we rearrange this a little bit, we'll get the formula we're about to see. The 1/2 times the apothem times the number of sides times the side length. This little guy here is also known as the perimeter. So you're multiplying the perimeter times the apothem and dividing by 2. That's exactly what this says to do. So the apothem, or the area, sorry, is 1/2 times the apothem times the number of sides times the side length, or 1/2 of the apothem times the perimeter. So we have another hexagon. Again, the nice thing here, I mentioned it earlier, that hexagons make nice 6 equilateral triangles. So that means that the radius is also 5 with all these. We don't have the height though, but the nice thing here, again, this is why you need to know the central angles and how to find the interior angles. So the interior angles of a hexagon is going to be the number of sides minus 2 times 180 divided by 6. So that's 4 times 180 divided by 6. Four times 180 is 720, and divided by 6. We get 120. Well, that's the entire interior angle. It's being split in half. So really, the angle inside here, so that is this whole angle here that we just got. If we divide that by 2, this is also 60, which means this one up here is 30. We made a 30, 60, 90 right triangle. So there's our triangle that we're looking at. Again, it's a right triangle. We have the hypotenuse. We need to know, well, really, we don't need to know the bottom part. The base of it is 2.5 because it's just half of the hypotenuse. But we need to know what this other side is. That's the apothem. So we need to use our knowledge of 30, 60, 90 right triangles. Going back to last semester. So if the bottom one is x and the hypotenuse is 2x, the other one is x times square root 3. So that's just going to be 2.5 square root 3. So our apothem is 2.5 square root 3. My 5s are always sloppy. So now we have our apothem. It's a hexagon, so we know we can go ahead and just multiply by 6. So now let's use our formula. So the area of a hexagon is equal to 1/2 of the apothem we just got, 2.5 square root 3, times the number of sides, 6, times our side length of 5. So that's going to make it about, so the 6 times 5 is 30, 30 times 1/2 is 15. So it's 15. No, you're not going to do that. All right, so sorry, I wrote it out a different way on my cheat sheet. So just plugging that in the calculator. So it is 15. 15 times 2.5 will be 37.5 times the square root of 3. Which is the nice not rounded number, but it does say to round to the nearest tenth, so we'll go ahead and plug that in the calculator. And our area for our hexagon comes out to be about 64.95, so really it's just 65.0 square meters. So these can definitely get more complicated when they're not just hexagons. So the nice thing about a hexagon is that we know that they make 30, 60, 90 triangles when you split the equilateral triangles in half. Not so much the case when you have a pentagon. So now we again need to find out what those interior angles are. But this time they're not necessarily, well, they'll still be getting divided in half, but they're not going to be nice and pretty where we can use our 30, 60, 90 special right triangles. So we might have to use some trig here, unfortunately. So we are again missing our apothem. So we need to actually figure out what our interior angle is. So the interior angle of a pentagon is now 5 minus 2 times 180 over 5. 5 minus 2 is 3. 3 times 180 over 5. 3 times 180 is 540 over 5, which comes out to be 108. Again, that is the entire thing, though. So we need to divide that by 2 and get our 54. So our right triangle looks like this. There's a right angle. We know that hypotenuse is 9. We don't know what the bottom part is either, so we actually need to figure that out as well. Because that is 1/2 of the base. We got the height. Or 1/2 the, let's rewrite those in terms of or a pentagon, not a triangle. So we're missing the apothem and 1/2 of the side length. So we got a few things to figure out here. So we're going to use some trig. We have an angle. We're missing the opposite and the adjacent sides. We have the hypotenuse. We have to use sine and cosine. So SOHCAHTOA, let me write that out. Bring us back to last semester even more so. And so sine of our 54-degree angle is equal to, so the SO part, is the opposite over hypotenuse. So our opposite side is the apothem over 9. So our apothem is equal to 9 times sine of 54. I'm not actually going to figure it out. I'm going to leave that as it is. So I don't have decimals rounding now. I'm going to leave it just like that. Then we also have to do the cosine part of our 54, which is going to be equal to our half of our side, 1/2 of our side length over 9, the hypotenuse. So we multiply again, we get the 1/2, so we're going to have to multiply by 2. So it ends up being our side length is going to be 18 cosine of 54. So now, again, I'm not going to figure that out. I'm going to leave that as it is and just use these as they are in our equation for or the formula for our area of our regular polygon. So the area of the polygon, in this case it's a pentagon, is equal to 1/2 of our apothem, which we just got is 9 times the sine of 54. Shift this down a little bit because I'm going to run out of space on that line. Times The number of sides is easy, that's 5, times our side length, 18 cosine of 54. Now, at this point, my suggestion is just to plug it all in the calculator. You can multiply 9 times 5, get your 45, 45 times 18, and then divide on whatever you get by 2, or really it'd be, I guess, 9 times 9, 81 times 5, so that'd be what? 405? Anyway, but then you still have to multiply by sine of 54 and cosine of 54. So at this point, the best, actually I have it written down that it is 405, I didn't even realize I did that. So 405 sine of 54 cosine of 54. So at this point, it's time to plug them in the calculator. Whatever calculator you use, make sure that the mode for this is in degrees. If it's in radians, you're going to get the wrong answer, and then I can't help you there. And it depends on the calculator you're using too. Various calculators have various ways to do that. So rounding to the nearest tenth, we get our final answer of 192.6 square centimeters. Now again, I didn't round it all because I want to make sure that this exact answer is correct. If I rounded earlier, and I rounded both those answers to the nearest tenth, my numbers might be off a few decimals, or even a whole number. That's not okay, especially when you're dealing with real-world things. This obviously is just a regular old pentagon, but if, say, I'm building a building that's a pentagon, I want to know supplies that I need. So I want to make sure that I get those calculations correct. Don't round early. Rounding early can kill people. No. Save lives, round at the end. So, we got 2 more problems to take a look at. The next one is our first composite. So, getting away from our polygons now. Not as difficult anymore. We just have to do area a few times and add it all up. So, here we have this irregularly shaped pool. We want to find the area of the surface of the pool. So, it's got, looks like 2 half circles that are the same circle. So, we're going to just say that's one circle. And we have a rectangle and a triangle. So, first things first, the rectangle is the easiest one. That's just length times width, or base times height, if you're looking at it as it's a parallelogram. That's going to be 32 times 16, and that will get us 512. Then we need to look at the area of the triangle. I don't know why I'm writing it out. I know that I like to do the symbol. Base times height divided by 2. So that's going to be the 15 and the 32 are the numbers that go along with it. And it doesn't matter which one you put where, you're just multiplying them together anyway. So we'll just say the 32 is our base, the height is 15, and we divide by 2, and that gets us 240. And finally, the one that's going to give us a decimal, the area of the circle, or the 2 half circles, if you want to do it that way. You can do it individually, but that's kind of repetitive. Pi r squared, pi times 16 squared gets us about 201. It doesn't say where to round, so I'm going to go to the nearest thousandth because that's what I like to do. 0.62. So all these are feet squared. Doesn't matter so much to do that in each one. Now we need to add them up. So when we add all these up, we get our grand total of 953.062 square feet. Not too bad. This last one, though, is a little bit different. We actually need to find the area of the whole thing and take away that middle part that's not shaded. So we have to find the area of 2 rectangles, basically. And so our first one, that little one inside, one we're going to take away is 100 by 20. That one's easy. And then the entire thing, we don't have the entire length, but we know that it's 25 on the top part, it's 25 on the bottom, and it's 20 in the middle. So that's just going to be 20, 25, and 25, or 70. And we do the same thing on the other side. It's 25, and it doesn't show it, but it's 25 on both sides of that hole. So 25, 25, and 100. Or 150. So the area of the shaded part, shaded rectangle. Well, let's area of the whole. is equal to 150 times 70, which comes out to be 10,500. Then the area of the hole is going to be 100 times 20, or 2,000. And we need to subtract here because we're taking away that unshaded part. And that gets us a grand total of 8,500 square feet. And that's it for these notes. See you next time.